Log on, tune in, find out. Another good idea from Cambridge.
My name is John Roberts from the University of New South Wales in Sydney. He'll be talking on symplectic structures for difference equations, including integrable maps.
Okay, thanks very much, Rod. Also, thank you to the organisers. It's very stimulating and enjoyable workshop, so certainly enjoying myself very much. Okay, this is joint work with Reinout, and is sort of being written up as part of the time here. So let me first put this into some sort of context. So imagine we have a Hamiltonian system. And just because of the way, the idiosyncrasy of the way I do this, x is in Rn plus 1. I'm not considering this to be even dimensional, so more generally, I'm considering the case of a Poisson structure. And so the idea is that the differential equation, or the flow, is being generated by a Poisson bracket, and the Poisson bracket is encoded by this Poisson structure matrix, omega, such that the Poisson bracket of two functions involves omega in the following way. And the entries, therefore, of my matrix are just the fundamental Poisson brackets. Okay, so what sort of structure matrices can you have to define a Poisson bracket? Well, you need that the matrix omega is skew symmetric. And with this definition of Poisson bracket, I need the Jacobi identity, which is a condition involving the derivatives of the entries of omega. In particular, if omega is constant, I only have to worry about skew symmetric. So any constant skew symmetric matrix can generate a Poisson bracket in this way. And the associated flow to this map, the associated flow to this vector field is satisfying, which I'll call phi sub t, is satisfying the following matrix relation. Okay. So that's what the flow is satisfying. Okay. What I want to consider, because this is a discrete integrable system, workshop, is I want to consider maps where the image point I denote x prime, and I want them to satisfy the same thing as the flow here. In other words, I want them to be symplectic homomorphisms. So now I can put omega prime, whereby I mean Lx. So I want to explore this relationship. If omega is constant, then this side will just be omega again. Omega prime will be this. And in particular, I want to consider a special kind of map, one that has come from a difference equation. So let's imagine we have an n plus 1th order difference equation. then this means that my map has a simple structure where the only non-trivial part is the function g that comes into the last line. So if I switch to my notation, then my related map is this one. So what I want to do is I want to consider this relation for this type of map. I want to build a symplectic structure. I'm going to restrict for the most part to omega being constant, in which case I only have to enforce that I have a skew symmetric matrix, but I'll make some comments along the way. You see some relations that must hold if omega was not constant. And so far, because I haven't restricted the dimension to even or odd, I'm building a Poisson structure. But if I now demand that omega is non-singular, I get a non-degenerate Poisson structure. So I have this forces me to now be an even dimension, because remember this matrix is skew symmetric, so in any odd dimension its determinant is 0, and then I will have a symplectic structure or a constant symplectic structure. Now, why is this of interest? Well, if we were going to look at the Liouville integrability of discrete maps in even dimension, then they should be, the map should be symplectic, and they should have, let's suppose the dimension is 2k, they should have k integrals in involution with respect to the Poisson bracket. And we've already seen some talks where people find systems, they find integrals. It's very suggestive of integrability. It's sometimes hard to find symplectic structure or even the Poisson structure. There are other approaches to this problem. You can try and find a Lagrangian approach. So you can try and find a Lagrangian for the map, and that structure builds in and enables you to perhaps go this way. But on the other hand, finding Lagrangians for difference equations is itself an area of research. So I want to do this problem for difference equations, but I'm motivated by certain forms of difference equations. So, I don't know, I hope that is sort of somewhat readable. Here are some special forms of G. And these are related to travelling wave solutions on quad graphs. So this is one way that you can associate, you can generate difference equations that may be integrable. And so people have spoken about this. But imagine you have a partial difference equation, so you have a quad graph, some rule for it. But now you specify a staircase of initial conditions so that you can propagate this rule throughout the plane. Various authors have looked at this and have looked at the sort of rule that you should have. Consistency around a cube, for instance, that is going to suggest integrability. However, one thing you can do is that you can reduce this partial difference equation to an ordinary difference equation of the type L, if you like, or the line just above it, by doing a travelling wave reduction. So in other words, assume that L and M in the field just enter by this travelling wave ansatz. And Z1 and Z2 are coprime integers. That enables you to represent 1 here and then to put a label on everything in the staircase. So this will lead to a hierarchy of difference equations in Z1 and Z2 being the parameters. And some of the integrals have been found for this explicitly in recent work by Peter van der Kamp and Omar and other people associated in the Reinhardt group. But what is the symplectic structure if you really wanted to show Liouville integrability of these things? So here are I call them type S and type K. These are difference equations. So for instance, type S just looks like this. G is minus the first variable, which is V0, plus some function of Vz1 plus Vz2, where Z1 and Z2 are these integer coprime integer parameters. And now let's assume that I'm n plus 1 is 2k, so I'm an even dimension.
John,
Yes.
are you sure that the thing is well focused? Because I have difficulty.
I'll try.
It's very pale.
Helps a little bit. Yeah,
Help a little bit.
helps a little bit.
Okay. Do you want me to tell? Oh, it helps you. I can easily do this. So, for instance, let's just consider this. So let's imagine the G is like this. Okay. With Z1 plus Z2 adding up to 2k, some even integer. Now, even though I said I'm going to consider a constant symplectic structure, there is an exponentiation process that relates this left-hand map to another type of difference equation where now the G, so now suppose I let V sub I equals e to the little vi, so I make a change of transformation from here to here.
Sorry, I was just wondering about your notation.
Yeah.
V sub Z1 means what?
These are now my variables. When I write the map here, my variables are V0 up to Vn.
I understand.
This is just the
So
variables.
Z1 is just an integer, isn't it?
Z1 is an integer. Yes, exactly. So every time you give me Z1 and Z2 adding up to 2k and they're co-prime, you've generated a particular instance of this L. Yep. Okay, but now I want to point out that even if you look for constant symplectic structures, you get something for free under this exponentiation process. So that if you do this exponentiation, it's pretty clear to see that when you walk through here and exponentiate both sides, you again get a map of the type L, but now it's in capital V, and the last line will change, your G will change, and you will find that your new V looks like this. It will be e to that G, and then inside you will replace all the V sub i's by their logarithms, but given that you have a sum of logarithms, it'll become log of a product. You can absorb that into the arbitrary function, and so what you'll get here, this comes from exponentiating this, and then you'll get some other function, I'll call it capital F. It'll be a bit messy, but we don't need to worry about it, and so you'll get this. Okay, so this is another difference equation. And what happens is that the constant symplectic structure over here gets turned into a non-constant symplectic structure here, where this is the entry in the symplectic structure. Okay, this is sometimes, I think, called by the physicists a Wahl bracket. And in a recent paper I saw on cluster algebras and Poisson structures, it's called the log canonical Poisson bracket. Okay, so we're going to get some results from considering constant things. We're going to be able to get some payback for non-constant ones. Another example here, and again, it doesn't really matter so much the details, but here is another example of a G minus V0 minus sum of various V sub i's, again involving my integer parameters Z1 and Z2. Straight away, for a particular type of F, this relates to the KdV difference equation. And again, by exponentiation, it relates to this form of the MKdV. Okay. So the basic message is, by working out constant symplectic structures here, we'll identify non-constant symplectic structures of this Wahl type for these things. Okay. So, let's write out what this relation gives us. And for the moment, let me take omega constant, but I'll make some comments if omega wasn't constant. Okay. So, by working on both sides of that equation, we learned that the map L of the type we've taken has a constant symplectic structure if and only if the matrix is skew symmetric. Well, we were obliged to take skew symmetric, but it's also turplets. So it's defined in diagonal bands. The principal diagonal, of course, is all zeros, but it's generated by the first row, because once you choose alpha 1, you continue it all down here, alpha 2, continue it down here, and so on. So it has this banded turplet structure, and of course by the skew symmetry I just take the negative of the diagonals heading out the opposite way. And then I have this set of bilinear equations that relates the unknown alpha 1 to alpha n, and then the derivatives of g. Yeah, so g sub I is dg dvi. And what I'm interested in doing is, for a given symplectic structure, finding the g, and for a given map, finding if there's a constant symplectic structure. Okay. Now, suppose you do this exercise and you don't assume that in relation star up here the symplectic structure is constant. Then what happens is that your omega that's allowed here is still determined by its first row, but what happens is that as you come down the diagonal, you have to take alpha 1 evaluated at the first iterate of the map, and then you come down again, you have to have alpha 1 evaluated at the second iterate of the map, and so on. So in the first row, alpha 2, and then you just generate the next entry by alpha 2 evaluated at first iterate of the map, and so on. Alpha n is the only one in the corner here that you don't have to do that to, so that's what it looks like. And then on this side here, I have to put the functions evaluated at iterates of the map. The easy way to remember it is such that the bottom index and the top index just add to 1. Okay, so here the top index means alpha n minus 1, all evaluated at L of x. And you see, for instance, that this bracket immediately satisfies this relationship, because as you come down the diagonal and you go I plus 1, j plus 1, then you see that that is exactly what you get by stepping up the map, because that's the first sort of trivial part of the advancement of the map. Okay, for notation, I introduced this column vector alpha 1 to alpha n, so that really encodes my symplectic structure, constant symplectic structure, and its reverse, so written top to bottom, I call alpha hat. Okay. So the first thing I want to do is I want to consider that I'm given a symplectic structure, and I want to determine all difference equations that have that symplectic structure. Okay, now here's the punchline. Okay, and let me say something about the structure here. I can break my problem into a homogeneous part. There's obviously linear structure here, so let me call the homogeneous problem when this right-hand side is set equal to 0. And then a particular part, which is a particular solution of this. So remember now, the idea is that all the entries of omega are now specified, or equivalently, all the entries of this vector alpha are specified. Okay, then the G must look like this. It has a homogeneous solution which looks like this. Some arbitrary function times evaluated at a linear combination of the V's excluding V naught. Okay. The W sub I are constants which are generated by taking determinants of the known symplectic structure. I'll describe that in a minute. And then a particular solution is given by minus V naught plus another linear combination specified by these Z sub i's. Okay. So there's an arbitrary function here, f. So there is a whole class of difference equations, or a whole class of G's that have this given symplectic structure. As to what the omega sub i's and the Z sub i's are, they're actually given by, effectively, you set this up so that you can use Kramer's rule, or Kramer's rule perhaps. Okay, and the way you do this is that you realize that what you've written out over here, this equation here, is n equations, but my omega is n plus 1. So actually what they are the bottom suppose I consider this problem. So r is some unknown function. This is the 0 vector of length n. And remember, omega is n plus 1 times n plus 1. Then this equation that I have up here for the homogeneous problem is just everything but the top row of this. So I've embedded the problem in something which now is square. That's the trouble with this. The dimensions aren't right. So now, if I can solve this for any r, it must include the solution of the problem I'm after. But now my assumption is that this determinant is non-zero, so I can just write out what the w's are using Kramer's rule by just substituting this column in appropriate columns of this side. And given that I've got an arbitrary factor to play with from linearity, I can actually drop the r, which is common to everything. Yeah? So the solution of this is omega sub I is equal to and then a particular determinant here, which is take the determinant of omega, but put this in the I plus 1 column. Okay, by Kramer's rule. But of course, I can then expand along this column. R will come out as a factor in all of these things. I can get rid of it. And so the nuts and, or if you like, I can absorb it into the arbitrary function f. So I'll then call that little w. So w sub I is the cofactor omega 1 I plus 1. In other words, the sign determinant from omega obtained by deleting its first row and I plus 1 column. To get the particular solution, I just do a similar trick. I just build another problem of the right dimension. for the particular solution on the right-hand side, I have a vector which is alpha written bottom to top. So that's here, n by 1. And then I can just put 0 here. Again, because of the assumption on the omega, I can use Cramer's rule to expand this. So once I'm told the omega, I can generate this subsequence omega I and z sub I, which are the only unknowns in this form. And then I observe that if I do this for some cases, I observe some symmetries in the variables. So what I observe for a start is, it's not clear yet, but this is -1. The coefficient of this is -1. And then I also observe that these vectors, wi and zi, have a symmetry property, that they're invariant under reflection about their midpoint. So that's all this says. In other words, omega hat star is omega star. So what I'm saying is that omega is the vector of numbers omega 2k minus 1. Omega 1 is omega 2k minus 1. The second entry is the second entry from here. So I have this symmetry property. And then you observe that, and then you think about where that's coming from. It's actually coming from a property of the Toeplitz nature of omega. So then, if you now make the additional assumption that omega star has rank n minus 1, so remember, omega is assumed to have a non-zero determinant. Omega star is this minor here, the principal diagonal minor here. It's got odd dimensions, so its determinant is certainly 0. It's n-dimensional with determinant 0, but if you assume that it has full rank other than that, then you can show that indeed the W and the Z have these claimed symmetry properties. Okay. So this is a characterization of the difference equations that have this property. And once you have that, you can just start cooking up patterned symplectic structures and deduce what the corresponding omega sub I and z sub i's that you have. And some of these include symplectic classes that are in symplectic. You don't have to worry too much about the details, but here then are particular types of generating vector for the omega that we build up. The last entry in the symplectic structure is actually a free parameter, and so therefore there is a whole family of symplectic structures here for which this map has that symplectic structure. And some of these have sort of been found or conjectured by various people, including a former student of Apostolos Iatru, who looked at some sort of pattern cases and made some conjectures, but with this sort of device you can sort of prove what the Wi and Z sub i's have to be. Okay. Okay, let's take the converse problem. Suppose you're given a map, a difference equation, and you want to know if it has a constant symplectic structure. Well, as long as you're prepared to accept the sort of full rank condition that omega star has this rank n minus 1, then automatically you're going to be forced to study maps of this form. And so now the idea is, suppose you're given a difference equation where now the W sub I and the Z sub I are actually given to you. They're strings of vectors, and you just insist, you just make up their entries, but you just insist that they have this mirror property. So what is the symplectic structure that then follows? Well, basically this problem, which we've turned into a problem in linear algebra, just has to be inverted. So these are the sort of, this is the linear algebraic structure. So in the previous case, we were given this matrix omega star, and if you like, this is how we solved for the W and the Z. But now we're assuming that we're given a W and a Z that are vectors with this mirror property, and therefore can we work out the symplectic structure? Well, then you go through the linear algebra of this. I don't know that it's so edifying, but ultimately what you do is you turn this into a following problem, another linear algebraic problem. From the known W and Z, you build yourself a matrix which depends on these known entries, and it is equal to this. So you want to find this vector alpha 1 through to alpha 2k minus 1. So this is a matrix, this is 2. This turns out to be 2 times k minus 1 equations in 2k minus 1 unknowns, which is the entries of alpha. So I get a freedom here, assuming that the determinant of C is non-zero, which precisely corresponds to the fact that, of course, my symplectic structure is only known up to an arbitrary constant, because I can multiply everything by that. And so therefore, if you're now given something of this form with the specified Z sub i's and omega sub i's, then you can form this matrix, and provided its rank is equal to 2k minus 1, you can generate the entries of your symplectic structure. Okay, so you can put this on a computer and just generate what the symplectic structure is. However, some of the maps that we're looking at in integrable systems are highly patterned. So you'd expect that the symplectic structure that you get is also highly patterned. So for instance, they're highly patterned and they're also quite sparse. So for instance, let's go back to this type S, which looks like this, and we had it up here. So if you look at this form here, what do you have? You have that the Z sub i's are all 0 for this. And then here you have most of the W's are 0 except for these, and these are opposing each other with the right symmetry. You can just check that, it's a condition on this. And so therefore you can surmise what you think is the generated symplectic structure for this. And then by induction you can sort of establish it. And similarly with this KdV form, and by what I said earlier, under this exponentiation you then get this Weil Poisson structure, non-constant Poisson structure for the result. So just to give you a flavour of that, let me show you what the result is for type S. Okay, and as I said, previously some people have looked at this problem, for instance, with Z1 equal to 1, which is a type of the staircase. But now, in the general case, you can do the following. You're given a dimension. Okay, so what are your parameters? You've got a dimension 2k that you're looking in. You're given this map. You're given Z1 and Z2 coprime. In this case, such that Z1 plus Z2 minus 1 is 2k. And then you can show that if the greatest common... So the first thing you do is you take the k that's in the dimension and you calculate it mod Z1. So you choose a Z1 and then your dimensions are going to go into residue classes determined by what k is mod Z1. Okay. If the GCD of R and Z1 is 1, which I think is generic, and I must say I'm sort of, as I said, I'm writing this up right now, so I'm sort of checking some of these things as I go, then it turns out that this first row of alpha that you want to generate, so remember this is going to be alpha 1 up to alpha 2k minus 1. Although k could be very large, everything just depends on what its residue is, mod Z1. And then this first row is actually generated by using a generating block that goes alpha 1 up to alpha 2Z1. And with this generating block, you just repeat it as many times as you can to fit into the first row. And then to actually generate the block, you play this game according to these rules 1 and 2. So to make things clear, let me give an example. Suppose I take Z1 equals 5. And let's suppose I take, say, k equals 2. Yeah? So that could be dimension 12. Or it could be dimension 24, for instance, or it could be an infinity of dimensions, all those that for which k is 2, mod 5. And so then I know I have to generate a block of length 10. And this tells you what the rules are. The first rule says that you put a 0 in the last entry, and then you subtract off in units of 2r. So here, r is k mod Z1, so here r is 2. So what you do, let me actually try and set this up. Zero. You go back every 4, so 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Is this right? Yep. Until it will exhaust itself. And the second thing is an alternating minus 1 plus 1, where you start at Z1, so you start at alpha 5, and then you subtract again off lots of 2r, which is 4, and at the first thing it's always a 1, and then you've just got to remember to change the sign. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then 1, 2, 3, 4. Yeah. Let me check. Yeah, that's what you do. And so now, if k was 3, r would be 3, and you just play the same game, but you go off in blocks of 6. So this is sort of a number theoretic, if you like, or algorithm to generate the entries of your symplectic structure. A similar thing can be done for the second thing, the KDV, and there also the MKDV, but I'm not totally prepared to sign off on that quite yet. So it's being worked out now. Okay, I think that's it actually.
Any questions?
Assume that you know that you have a map that's integrable, and this procedure gives you a symplectic structure. This actually not help a lot in finding also a Lagrangian formulation for it. Because really, then you know what m cross m, m referring to the first half of the positions, should have a symplectic structure. And the Lagrangian should give you, via the Legendre transformation, the p cube, the xp structure that is canonical. Right? I mean, this is this Veselov diagram. And the omega should arise by pulling back the canonical symplectic structure on the phase space that you're looking for, back to m cross m. But now you know what omega is, which of course is just a difficulty if you set up a Lagrangian description that you don't know that.
Well, I think I'm smiling at Peter Hayden because we're roommates and we have been talking a bit about the sort of cross implications of the Lagrangian with this. So yeah, look, I must admit, you know, I think there are, well, Peter maybe can say more, but I would hope this does give you some leverage there.
If you have a Lagrangian, you know actually more. That's what you mean.
Yes.
You can use this Veselov projection to XP phase space, and you have actually Hamiltonians on those phase space for
Yeah.
variables.
Do you know I mean, is the Lagrangian clear for an arbitrary difference equation?
No, that's just what this might
Well,
help.
exactly.
It might help a lot if you know this.
Well, in a sense, we're looking to meet halfway because we now have some difference equations where we've sort of independently come up with the Lagrangian, or guessed it if you like. And there must be some way of sort of checking these two off each other.
I mean, what I'm really saying, if you have the Lagrangian gives you omega. Right?
Yes, exactly.
But here you have omega, so you might be
Turn it
helped
the other
to
way
find
around.
out if there is one.
I think I'd just add as a comment that what we've been discussing has been multiple symplectic structures. So John has been looking at one type of symplectic structure, and I've been looking at another that's come from a Lagrangian, and they're quite different. The ones I've been looking at depend explicitly on the form of functions in the equation, as yours doesn't. Is that right? In certain parts of the equation. So it's clear that they're very different.
But
symplectic
there's
structures.
some kind of bi-Hamiltonian structure.
Something like that, yes, exactly.
Which ties in with the integrability.
Yes.
But I mean, these structures that you're getting are coming for a whole class of things independent of f, right? And the integrable case is only a very special type of the function. Yeah, so.
Related question. You talked about constant omegas. So I suppose you can relax this constraint.
To some extent you can, because you can follow through and you can, as I said on the this slide, here is here's what happens if you want to relax the constant. You're now looking, you're still looking for some functions, alpha 1 to alpha n, from which this tells you the prescription to build the omega. And now you want to satisfy this. You can still use this sort of embedding trick into the right dimension. And now you'll get, whereas previously when you solved for these w's, they were just constants. So that when you integrated them, all you had to do was add that as the coefficient. Well, this is wrong actually, but I mean, wi is a number, so you integrate this and then you get the linear combination of wi times vi, etc. Now you get a system of first order partial differential equations, yeah. And yeah, I don't know how, I'm actually seeing, as I sort of go, how far I can push that. I don't. I'd be surprised if I can sort of push that the whole way.
Yeah, one more question. If you take the symmetric QRT map, they have k equal to 1, is there a Lagrangian description there? See what I mean?
I don't know of one.
Oh, I'm asking.
Yeah, yeah. Well,
It's a natural question, don't you agree?
yeah, yeah.
In that case, you know omega, don't you?
Yes, yes, yes.
That should help.
Yeah, yeah. Okay, well, I need to talk to you about that. That sounds. I mean, there's not a Lagrangian for the QRT as far as I know.
I seem to remember there is actually, but I'm insufficiently sure of myself to commit myself on that. But yes, I think there is. But of course, it's not necessarily the same symplectic structure.
Yeah, but for Macmillan there is.
From Macmillan,
Yes.
So you would expect it to be one with symmetric QRT as well.
Yeah. I have a feeling there is.
Well, that's Franklin, Vasilis, and Hans, isn't it?
Not quite.
Not quite.
Okay, so let's thank John again.